To know Navier-Stokes is to know the mind of God. The Navier-Stokes equation. This strange-looking line of symbols describes everything that flows in the universe. That includes water, air, honey, gas, smoke, everything. You may have heard of it because there's a $1 million prize for anyone who can prove that this equation has a solution. So what does this equation do for us? Say you're pouring water from a cup and you know what it looks like at one point in time. If you plug in all this information into the Navier-Stokes equation, it'll predict how the system will evolve for all time. It's like taking this freeze frame and hitting play. So the $1 million prize is for proving that given any initial condition, the Navier-Stokes equations will spit out a solution that will last for all time. Okay, why is this so hard? Well, the first reason is fluids are really complicated. Just take a look. The water here doesn't flow in a smooth fashion. It seems to go in some places and go out in other places. There are some air bubbles caught in between as well. And if you look at the water in the cup, there are little swirls and eddies that are forming already. This seems so random, so unpredictable. How do we get a handle of this? Well, you might say, okay, but that's not our job. We already have the equation. The hard part is done. All we need to do is solve it. Unfortunately, that's also really hard. To understand why, we only have to look at these two terms. This term is the good guy. It's called the diffusion term. This term is the bad guy. It's called the convection term. When this guy is much bigger than this one, you get nice, smooth flow. But when this guy is smaller than the other one, you get erratic, turbulent flow. This equation, therefore, is a constant push and pull between these two extremes. If we just deleted the bad term, we'd be able to solve the equation in minutes. Of course, we can't just do that, but we can do the next best thing, make the bad term as small as possible. That is, look at cases where the diffusion term is a lot bigger than the convection term, and there are two cases in which this would happen. 1. If the fluid is very slow. Here, the velocity v would be very small, much less than 1. So the convection term would be like v squared, which is much, much less than 1. In this case, the good guy overwhelms the bad guy, and we win. This was the result of a groundbreaking paper in 1964 by mathematicians Fujita and Kato from Japan. They proved that if you start off with a slow enough velocity field, then there exist smooth solutions to the Navier-Stokes equations. Now, the definition of slow enough is quite technical, but that's what the paper's for. 2. The fluid only has turbulence at a small scale. That is, you can only see the turbulence if you zoom in really close. What would we expect if we pressed play? Well, we'd expect all of these super small wrinkles to even out. This was published 30 years later in a 1994 paper by these French mathematicians, whose names I wouldn't even try to pronounce. They proved that if your velocity field oscillates really fast by a huge amount, the diffusion term dominates and we find smooth solutions to the Navier-Stokes equations. But this only deals with some special cases. We eventually have to confront the monster. The main strategy people are using to do this is a branch of math called functional analysis. Here you study Hilbert spaces, linear operators, Lebesgue measure, inner products, the whole deal. These tools allow you to compare functions with other functions. For example, we know what it means for a number to be bigger than another number, but what does it mean for a function to be bigger than another function? This is exactly what we need to gauge the size of the convection term. Mathematician Olga Ladyshenskaya used a series of intricate inequalities to bound that term by a series of linear, simpler terms. The result was spectacular. The Navier-Stokes equations were solved in 2 dimensions. Unfortunately, the argument collapsed in 3 dimensions, so we were back to the drawing board. Since then, people have tried many other strategies. They've tried solving an easier version of the equation called the weak Navier-Stokes equation. They've tried using differential geometry to show that fluids traveling in certain paths have solutions. They've even tried using probability to guess likely solutions instead of the solution. But so far, nothing has turned out correct. Now that we've seen the nitty-gritty of it, let's look at the big picture. On one hand, we can think of this as just a math puzzle trying to solve an equation, but really, it's something much more profound. My physics professor in second year put it like this: solving Navier-Stokes is like solving someone's personality. This equation describes everything that flows, ever. Air, water, ketchup, gas, smoke. A solution to Navier-Stokes means that there is one and only one function that describes all of these things at once. This is nothing short of solving a personality. A personality is just a bundle of neurons and synapses in our brains. Could we put these connections in a gigantic equation, which would determine exactly what someone will think and feel, like and dislike, say and do at any given moment? Solving Navier-Stokes amounts to doing this. There's something terrifying about that. About the fact that you can reduce nature to a clinical set of rules. But it goes beyond this. The core difficulty of solving fluids, their apparent randomness, their unpredictability, their chaos, is common to so many things. For example, how stock markets fluctuate, how gravity tugs on asteroids, how chemicals react with each other when they're unstable. So if we can see through the Navier-Stokes equation, we can actually see through the core difficulty that so many things in nature share. We can solve the personality of our world. Thomas Pynchon wrote, "All the stars must represent some single gigantic equation, to the mind of God as straightforward as, say, the equation of a sphere, but to us unreadable, incalculable." In a very secular sense, one can say, to know Navier-Stokes is to know the mind of God.